Ever wondered how your smart thermostat knows to crank up the heat when it's icy outside? Or how a hospital's monitoring system spots a patient's vital signs going off the rails? It's not just luck, it's machine learning working behind the scenes. Today, we're exploring a breakthrough called CaPulse, a super smart tool that doesn't just find anomalies, it explains why they happen. Let's dive in. Time series data is everywhere. Stock prices, weather patterns, your heart rate during a workout. But spotting anomalies here is like searching for a needle in a haystack. Traditional methods struggle because they're stuck on the surface, mistaking noise for signals. Imagine a doctor diagnosing a patient based only on symptoms, not the underlying biology. That's where CaPulse steps in, using causal reasoning to uncover the why behind the weird. Here's the problem. Anomalies are rare, labels are scarce, and data has overlapping patterns. Daily trends, weekly cycles, seasonal shifts. Traditional models treat these as static, missing the dynamic relationships between variables. CaPulse flips the script. Instead of asking, what looks strange, it asks, what's really causing this? Think of it as a detective who doesn't just examine fingerprints but reconstructs the entire crime scene. CaPulse tackles three core challenges through a combination of periodical normalizing flows and causal modeling. Let's break it down. 1. Label scarcity. It learns from unlabeled data, using self-supervised techniques to identify patterns without relying on pre-labeled anomalies. 2. Data imbalance. It focuses on deviations from learned causal structures, ignoring the normal noise that overwhelms traditional models. 3. Multiple periodicities. It disentangles short-term, hourly traffic spikes and long-term, seasonal trends, patterns using Fourier Transforms to decompose data into its rhythmic components. The magic happens with normalizing flows, a mathematical framework that transforms complex distributions into simpler ones. Imagine reshaping a tangled mess of strings into a neat, organized grid. CaPulse uses this to model how data evolves over time, creating a normal baseline. When deviations occur, it flags them as anomalies. At its core, CaPulse relies on two key components. PASIM, periodicity-aware causal model. This acts as a periodicity detective, breaking data into cycles. It uses Fourier transforms to split time series into frequency domains, isolating daily, weekly, and seasonal patterns. MPCF, multi-period causal flow. This layer weighs the importance of each cycle, blending them into a unified causal graph. It's like a puzzle solver cross-referencing clues to identify which patterns are critical. But here's what makes CaPulse revolutionary. It doesn't just detect anomalies, it explains them. By enforcing orthogonality loss during training, it ensures each learned pattern is independent, preventing overlap that could mask true causes. For example, if a server crashes, CaPulse can distinguish between a software glitch, hardware failure, or external attack by tracing causal dependencies in the data. The proof is in the pudding. On 7 real-world datasets, ranging from server logs to medical records, CaPulse outperformed existing methods by 3% to 17% in detection accuracy. But the real win? It's interpretability. Unlike black box models, it provides causal explanations, showing users exactly which variables triggered an anomaly. This transparency is a game changer for fields like healthcare, finance, and infrastructure monitoring. So what's the takeaway? Anomaly detection isn't just about spotting the odd data point, it's about understanding the story behind it. CaPulse bridges the gap between detection and diagnosis, offering a smarter, more transparent way to keep systems running smoothly. Next time you see a glitch, remember, behind the scenes, algorithms like CaPulse are working hard to figure out what's really going on. Thanks for watching. If you enjoyed this deep dive, hit subscribe for more explorations into the science behind the tech. Stay curious, and let's keep unraveling the mysteries of data together.